Hey everyone, and welcome to Dr. Abu RTN Academy channel. Today we are going to discuss part 2 of seminar 7 in the University of Debrecen on the subject of biostatistics. In this example, we are going to use z-test, to test the assumptions or the hypothesis and arrive to a conclusion. In this example, it says that a blood glucose concentration of students of the University of Debrecen follows the normal distribution. So this will be my population. It follows normal distribution with the standard deviation 0.4, sigma equals 0.4. It assumes that the mean of the distribution of the normal distribution, which is mu, equal 4.4 meter. A physician is taking a simple random sample of 16 from this population. So n equals 16. So he has taken a sample of 16 and he determined based on this sample that the mean blood glucose concentration is 4.65. So this is the mean of the sample, which is x bar. The mean of the sample, which is x bar, 4.65 mm. So here the first mean was for the distribution, that's why we put it as mu, and here x is the mean of the sample. The question is, can the physician conclude that at alpha, this is the rejection region, or the rejection percentage, that conclude at alpha equals 0.05 that the mean blood glucose concentration is different from the value 4.4, which is the mean, which I have here, So can he conclude that it is different or no? What is the p-value of the test statistic? So here I have to give null hypothesis and give alternative hypothesis and start testing the alternative hypothesis and see whether it is right or wrong. So I'll start working based on the alternative hypothesis and see whether the rejection region are met or not. If the rejection region met, this means the H null, the null hypothesis, it will be rejected. So my H naught will be, in this case, H naught, I'll put it as, I can choose whatever H naught I want, the H null. I can assume here, he is asking whether the physician can conclude that alpha equals 0.5, the mean blood pressure concentration, is different from the measure 4.4. So I'll assume the null hypothesis that the mean is not different, it is equal to 0.04. I can assume that it is different or equal. So I'll assume it equals to 0.04. So each alternative should be different from this one. So each which I'm going to use to work out. So I'll work based on each alternative, and I'll see if the answer or Z falls within the rejection zone, so H naught will be rejected. So I'll work based on HA alternative, and if the answer Z naught falls within the rejection zone, so Z naught will be rejected, not ZA. So ZA for the working, and the rejection or acceptance will be for H naught. So if here the hypothesis said that mu equals 0.4, so H alternative, that will be the one which we have here, the case that it is different. Different means not equal, so mu not equal to 4. As I explained in the previous video, I have three cases: mu greater than mu naught, or mu less than mu naught, or mu not equal. If mu if mu is not equal of mu naught, this means that mu has two values. Could be greater than something or less than something. So two distinct values. Two distinct values. Like here in the graph, it will be having 2, so it's not equal to this area. So if mu was greater than, for example, any number mu naught. So I'll draw the graph, distribution graph, okay, and this is the mean. I'll say it's greater than, for example, this value or this area, okay. So this will be the area. So in this case, my rejection zone will be to the right because it will be greater than. So the rejection zone will be to the right. So this will be my rejection zone. If I said that mu is less than mu naught, this means that, here is this one. This means I'm moving to the right. So assume mu naught is here, so I'll be moving to the right. So the rejection zone will be to the right, okay? So what if mu is not equaling mu naught? So the rejection zone in this case will be split to the left and to the right. So the 5% which I have here, alpha, will be split into two sides. Okay, I having two zones. In this case, I have one zone here and one zone there, to the left and the right. And each one of them will be 0.05 divided by 2. Alpha divided 2, okay? And here alpha divided by 2. So again, in order to conclude, if mu, we assume that HA, mu greater than mu naught, mu less than mu naught, mu not equal to mu naught. So in case of it is greater than mu, so we'll go to the right, but we'll have limit that this is the rejection zone, alpha, which has been given. If we will be going to the left, okay, so we'll have the rejection zone, which, because I will be moving to the left, so the rejection zone will be to the left. If it is not equal, so it will not be equaling this zone, okay, so it will be here, either here or here. It will not be equal this area, so it will be either here or here, the two sides. That's why alpha has to be split here. It's alpha divided 2 and alpha divided 2, and what we call two-tailed, okay, called two-tailed test. Here we have one right tail, here we have one tail on the left tail, and here we have two tails, okay, or two-tailed test. So I'll draw the curve, okay, and the mu will not be equaling, so this will be two-tailed, okay, it's not equal to this area in the middle, okay, so it will be either this side or this side. Then based on my alpha, so alpha will not be 5% on one side, it will be divided by 2, so it will be 0.5 divided 2 equals, it will be equals to 0.025 from this side, and this will be 0.05. This is the area, this is not Z, this is the area. This percentage, okay, which is 2.5 from each side, is the area inside, the probability, okay. So we can go to Z standard distribution table and find which value in the table is representing 0.025, which we can see here in this table here, which is equivalent to minus 1.9 and here 6, minus 1.96, okay. So here z equals minus 1.96, and here this is 25%. So if we go all the way up to here, okay, it will be 1 minus this 1 minus 0.025, which will be equal to 0.0975. So here 0.975. So also I'll go here. So the area up to this point, starting from here up to this point, it will be represented by 0.975. This will represent 97% up to here. So I have to find Z at this point. This is P, okay? So I have to find Z at this P, okay? At this probability from the table. So at P equal 0.025, Z was equal minus 1.96, which is this one. And at P equal 0.975, Z will be equaling, let us get it from the table here. Okay, it is here, so it will be 1.96 positive, okay? 1.96. So here Z will be 1.96, and here Z minus 1.96. So now I have got the Z values, Z 1.9 and Z minus 1.9, okay? So after getting the Z based on alpha, which we have to get the Z from this called Z critical, which is minus 1.96 and positive 1.96, okay? So we have to get that calculated from the formula, from this formula. In this formula, I have to substitute Z equal x minus mu divided sigma divided square root of n. This is x bar, okay, for the sample, and this is n for my sample, okay, and this 2 for the population. So just I'll substitute them. So putting x bar 4.65, okay, mu I have got it here 4.4, sigma 0.4, okay, then what you just have here, okay, and sigma 0.4, and then 16, n equals 16. So by substituting them here, we end up Z calculated equal 2.5. So now I have Z calculated equal 2.5, which is greater than the 1.6 which I have. So it already entered the rejection zone. So if it is equal, it's entered to the rejection zone, this means that the H naught will be rejected. So what was my H naught here? Oh, sorry, I have deleted it. My H naught was that mu equals 4.4. So since it is entered the rejection zone, so this null hypothesis is rejected. Okay? So null hypothesis rejected means that the mu is not equal to 4.4. And here what is the physician said? The physician said that the glucose concentration, the mean blood glucose concentration, which is mu, is different from 4.4, which is right. So here the alternative hypothesis is right, and it is the same as what the physician says. So what I can say that the physician opinion was right. So since we came in touch on these tables, okay, no need to stop here a lot. Just will mention that here we split alpha into 0.25 here from two sides. These are the areas, okay. So the area here up to here it is 0.25, and up to here. So this plus this 5%. So this is 95 plus 0.25. So the area up to here it is 0.975, okay, that's what you want to say here, and we get this point. So here we have mu was found 2.5, okay, 2.5. Let's use different color. We'll find 2.5, which is already inside the rejection zone, okay, the reject area. So here the statistical conclusion that the calculated value of Z, okay, Z calculated, okay, is in the rejection zone, so reject the null hypothesis. So we are using H alternative, okay, and if it came within the rejection zone, okay, so we'll reject the null hypothesis, okay. So we are using HA and we reject H naught, okay. So reject the null hypothesis and favor the alternative. Alternative was saying that it is the alternative was saying that it is not equal to, which is in matching with the physician decision. So the data here, the conclusion that the data which we have got, okay, support the researcher or the physicist hypothesis that the mean of the blood glucose is different from 4.4. So the case here that we reject the null hypothesis if the alternative hypothesis is true. Okay, type 1 error. So coming here to type 1 error, so in this case type 1 error means that we have rejected here our null hypothesis, so it is related to the null hypothesis. We have rejected the null hypothesis, but although we have rejected the null hypothesis, there might be something which is true in the null hypothesis. So when we rejected it, we have a little percent, maybe 1%, 0.5%, whatever the percentage is, which is small percent, which might be true. So by rejecting the null hypothesis, we may reject also something which is true. That's why it's called type 1 error. Okay, so type 1, we reject the null and it may have something true. Type 2, we accept the null hypothesis and it may have something which is wrong. But in our case, we have rejected the null. If we reject the null hypothesis, this means type 1, okay? And also by default, it might have little portion of it which is true. This is the end of the story of type A and type 1 and type 2. So now we knew that we reject the null hypothesis, and there is still a potential error which we must have it, because we have alpha, and the probability of committing type 1 error is alpha percentage. Okay, so the probability of having this error, type 1 error, will be equal to alpha percentage, not alpha divided 2. It will be alpha, okay, which is 0.05. The second part of the question was what is p-value. Okay, so based on our calculation, the z calculated, which is 2.5. Okay, this was the z calculated. Here it is 2.5. So we will go to the standard distribution table. It was minus 2.5. So we'll have z minus 2.5 from one side and 2.5 from the other side. So it's easy since our table is using from the left, from the minus infinity, okay, to calculate based on the minus 2.5. Okay, so here based on the minus 2.5, if we come to the table, minus 2.5, 0, it will be 0.0062. okay, and the same thing from the other side. So the probability will be the sum of them, this one plus this one, or one of them times 2. It will be 2 times 0.0072. So the total probability will be 0.0124, which is 1.24%. Okay, I hope this one is clear. By having this, we arrive to the end of the example solution. In this example, it says that the systolic blood pressure, okay, of a students of the University of Debrecen assumes a normal distribution with a standard deviation of 14. Okay, so this is normal distribution and this is standard deviation 14. A physician taking a sample of random n equals 12, okay, from this population, and determined that the mean of diastolic blood pressure is 96. So the mean equals 96. Okay, let's talk about the population also. That's why it is mean. Can the physician conclude that alpha equals 0.05? Okay, at alpha equals 0.05, that the mean diastolic blood pressure is larger than 90. So here we'll assume that mu is larger than 90. This will be the alternative, H alternative. Okay, so we always have H naught, which is opposite to what the researcher is proposing. Okay, so H naught, it will not be, so mu will be lesser than 90. Okay, or equal to 90. Okay, so the alternative, so we'll assume that the null hypothesis is opposite to or against to the researcher assumption. Okay, So H naught will be lesser than, because the assumption is greater than. So the alternative will be matching with the research, okay? And then we'll forget about H naught now, and all the working will be, as I told you, all the working will be based on the H hypothesis. So there are two things to keep in our mind. The first thing, that the H naught will be opposite to, or not matching to, or not in line with the assumption of the researcher, opposite, okay? And the alternative will be matching with it. So H alternative says that mu greater than 90. If mu greater than 90 here, 90 greater, so it will be the right side, it will be this side. So the 5% alpha, okay, the rejection will be on the right, because it's greater than 90. We are moving this side to the right, okay? So since our table is measuring from the left, the table which we have in University of Debrecen, some of the table is measuring from the mean and some of measuring from the minus infinity. The table which is given by University of Debrecen, so everyone has to make sure that he's matching with the table which he's using, okay? So this 5% means that if we measure from the infinity, we reach here 95%, okay? So up to this point, it will be 95% in order to get Z here. So we'll get Z at 95%. So if we go to the periodic table which we have, we'll find that at 95%, it is between 1.64 and 1.65. It is exactly in between. So we can use 1.64 or 1.65 or 1.645. Okay, I prefer to use 1.65, but here in the example, they're using, I think, 1.65. Let us see the next page. Yes, they're using 1.65. Okay, it doesn't make a big difference. So here at 95%, okay? So we can have 95% here or this one, any of them, so it would be 1.65. This is the 5%. So this is Z. Z critical, from the graph Z critical equals 1.65. So what about Z calculated? Let us come here. So Z calculated will be equal, Z equal calculated x minus mu divided sigma divided the square root of n, okay? And this x bar, okay? So I have x bar already, 96. Sorry, I have done here a mistake. This is the mean of the sample. He took a random sample of 12 of this population and they determined the mean. This is the mean of the sample. So this 96 is x bar. Okay, sorry for that. This is x bar, okay? So I don't have sigma. But since he gave me his assumption, the systolic blood pressure is larger than 90. So the mean, which he's assuming, okay, for his assumption, so this I can use it as my sigma, okay, as my standard deviation, because both of them will be picking from the same normal distribution. So here sigma will be 90. Sorry. This is mu, not sorry, I'm confusing. So this will be my mean, okay? Because this will be my mean, okay? So the mean, I assume the mean is 90 millimeter mercury, okay? So this will be my mean. So my x will be the x of the sample, x bar, the mean of the sample. So the sample, random sample 12, and determine that the mean of the systolic blood pressure in this sample 96. So this will be x bar. And then I don't have the mu of the population, okay? So he told me the mean, he assumed that the mean of the diastolic blood pressure for the population is 90. So I can use the same thing, okay? So I have mu here. So I can put x minus x bar minus mu, x bar equals 96 minus 90, which is mu, okay? Divided sigma, which is given 14, divided the square root of n, which is 12. So I get it 1.48. 1.48 means I have this one 1.65. So 1.48, it will be somewhere here before that. So it did not reach the rejection zone, okay? So H naught is not rejected. So the assumption of the researcher is rejected. So each alternative is not valid. Okay, the alternative which for the researcher is not valid, not working. Okay, and since it is not rejected, so the error which I have here, that it is not rejected, but maybe I have accepted it. Okay, so if it is rejected, it will be type 1. If it is not rejected, it will be type 2. Type 2 means that it is not rejected, but maybe I have rejected part of it. Okay, I have rejected part of it. So it's called type 2. So if it is rejected, the hypothesis is rejected, it will be type 1. If the hypothesis is not rejected, it will be type 2. So here, just as a confirmation, he said at 99. So here 1.65, which we get from the Z from the graph from alpha, and this is the Z calculated. So Z calculated before that, see the conclusion that the data does not support the research hypothesis. Okay, does not support HA. Okay, because H naught is valid now. Okay, because it doesn't reject H naught hypothesis. And we can copy this one from the question. Okay, does not the research hypothesis that the mean blood pressure is larger than 90 mm/gram. So this is type 2 error because it's failed to reject H naught. Okay, type 2 means that we cannot reject H naught, HNL. If we did not reject, it will be type 2. If we can reject it, it will be type 1. So type 1, rejection of H naught. Type 2, we cannot reject. Okay, failed to reject H naught when it is false. So it may be a false, H naught may be a false, but we did not reject it. Okay, it may be wrong, false, but we did not. That's why it's called error. Okay, this will be a very small or amount which is still available because this is just probability. Okay, so even if it is small, very small percentage, 0.001 or something, but it's still available. Okay, this is the type of error which may be here, that we fail to reject this, although it has some data which is false. It might have some data which is false. Okay, that's called this type B, a type 2. Then if you want p-value, I go to add the calculated Z 1.48, and I go in the table 1.48 and get the probability of it from the standard normal distribution table. Okay, so this is an easy step. But here, if I get it from the table at 1.48, this is 1.48, so it will give the probability to the left. So I don't want this one. I want the probability, okay, of this area, the rejection area which I have, okay, the rejection area to the right. So it will be 1 minus the probability which I got from the normal distribution, standard normal distribution table. Okay, 1 minus 9306. So the answer will be 0.0694. So when he asked me to determine the p-value, so the p-value for the extreme which is the side or that side or both sides if it's split between them. Okay, so this p-value determination, or for the probability of obtaining value of the test statistic at least as extreme to the right or extreme to the left or extreme to both sides. Okay, so it is not this area. Okay, in my case, the area which I'm focusing on to the right. Okay, it was to the right, so it will be only to the right. So I have to get here Z and get Z and compensate here, get the value of the probability, but this probability for this area to the left. So the area which is shaded here, the extreme area, it will be 1 minus this area. Okay, so it will be 6%, almost 6.9%.